All right, I think we'll make a start for the last session of the afternoon. Very pleased to introduce Vera Matarese from the University of Geneva to talk to us about space, the many substances.
Yes.
Oh, sorry, University of Bern.
Yes. Yeah, I was a little bit confused.
Sorry.
Well.
I'm new to Switzerland.
Yeah. So thank you, thanks Baptiste, Chris, the organizer, thank you Gaia, and thank you Shaxi for being my commentator. And yes, today I'd like to talk a little bit about the metaphysics of space. So my talk is a contribution in the metaphysics of space, and I feel that normally we have two different approaches in the metaphysics of space. So one approach is actually more metaphysical, and in this respect debates stand really on kind of alternatives, okay? So alternative conceptions of space, for instance continuous and discrete, and then we evaluate pros and cons, right? And then ask whether these alternatives are conceptually attainable, right? But then we might actually approach the question of what is the space from a more kind of physically grounded perspective. So we actually dig into general relativity, for instance, and then we try to extrapolate, to derive a metaphysical characterization of space, right? Well, then in this talk, I'm trying to actually bridge these two approaches, okay? So I will actually start with the metaphysical picture in the debate that opposes the continuous and the discrete view of space, but then I will actually be focusing on a particular discrete model that is inspired by loop quantum gravity, with a particular interpretation of canonical loop quantum gravity. And then from this model, I will ask questions, metaphysical questions, and I will offer some metaphysical characterizations of space that hopefully are new in the metaphysics literature. Okay, so first let me just say a few words about some definitions. What do I mean by discrete space? So I know that these definitions are not really accurate, but I think that they give you the kind of conceptual clarity that we need in this talk. So I claim that space is discrete if and only if for every partition of a finite extended regions of space into a countable number of regions of space, then each of these regions is composed of individuals or countable sets of points, and individuals and points are finite. Right? Then, if I say atomistic space, then it's a discrete, okay? But then a space is atomistic if and only if for every partition of a finite extended regions of space into a countable number of regions of space, each of these regions is composed of atomic regions of space. And these atomic regions are individuals, and a region of space is an atomic region if and only if it has no proper parts, so it's a mereological atom, okay? And of course these atomic regions are extended, so they are not points. Okay, so in the metaphysics of space literature we have this debate, right, that opposes the point continuous view of space and the atomistic discrete view. Atomistic here in brackets, because when we say discrete, I think that most actually understand atomistic discrete views of space, okay? And then normally we have a kind of standard winner. So we normally call the point continuous view as the standard one, the orthodox one, right? Why is it so? Well, for two different reasons. So the first reason is just, well, we have a very strong, well-developed physical theory of space called general relativity, and we know that space is continuous. The second reason is that, well, going back to Weyl, there is an argument against the discrete model of space, which seems to be insurmountable. Okay? So then what is this argument about? So Weyl in 1949 writes, so far the atomistic theory of space has always remained mere speculation and has never achieved a sufficient contact with reality. How should one understand the metric relations in space on the basis of this idea? If a square is built up of miniature tiles, then there are as many tiles along the diagonal as there are along the side. Thus, the diagonal should be equal to the length of, to the side. So here we have a portion of space right here, and then we can divide it in different miniature tiles, right? We can actually build a triangle here. We can draw a diagonal, right? And then if we count the length of the side and that of the diagonal, well, it turns out that we have 4 as the length of the side and 4 as the diagonal, right? So then this is the problem. This apparently rejects the discrete model of space because no discrete space can approximate the continuous space because the Pythagorean theorem fails in this kind of space, fails in the discrete model of space, okay? And so then we actually want a space, a discrete space that can recover the Pythagorean theorem and can recover actually the continuous space where the Pythagorean theorem holds, right? So what if we add more tiles, we make them tinier, tinier, tinier? Well, it doesn't work, okay? So then this is a wise argument. If a discrete space exists, it must approximate Euclidean space where the Pythagorean theorem actually holds. But discrete space does not approximate Euclidean space, so discrete space does not exist. And then we can make this argument even stronger if we think that what is metaphysically attainable, or conceptually, let's say conceptually attainable, cannot be empirical. So we can say if discrete model of space is conceptually attainable, then it cannot be empirical. The discrete model is conceptually attainable, so we should give up on empirical confirmation. We should not even go into the world and try to find a discrete model of space. Okay, so now let me say a few words about a Weierstrass argument. Well, it seems that there are different assumptions here, right? So the first assumption is, of course, that atomic regions of space in his model have the same shape and the same size, right? The second assumption is that the metric is such that each tile has the same number of adjacent ties. And then we have the third assumption, which is that the length between two atoms is actually measured in terms of the number of the atoms along the path connecting the two atoms, okay? So, of course, one could say, well, look, my dear Vi, we can just break one of these assumptions and then we don't have any problems. But then the problem is, so which assumption should be broken? Okay, so which of this is actually the one that we should drop? And it seems that here metaphysicians are in a certain kind of at loss in trying to work things out. And so trying to give up one or the other, and trying to check what kind of model can be actually derived from breaking these assumptions, one of these assumptions. And so, for instance, metaphysicians have been particularly obsessed by trying to violate the third one, so that we can actually calculate length in discrete models by counting the atoms along the path, okay, connecting two atoms. So, for instance, Chen in 2020 asked, why should we take that the length of a line is equal to the number of atoms of that line? Well, the question is, what is length and distance in a discrete model of space? What's the definition, right? So then she tries to justify this view, going back to a more fundamental principle, which is finite additivity. So she says, well, for any natural number n, for any n-dimensional region x, if x is composed of finitely many disjoint regions y's, then the measure of x is the sum of the measures of y's. And from this principle, we can derive another one, which is really a principle in standard measure theory, right? Which is a size by counting principle, which says, well, assume that every atom has unit size. Then finite additivity entails that the measure or size of a region is equal to the number of atoms it contains, right? And then from what we get, where we get from here? Well, Chen says, well, look, assume this principle of size by counting, right? Then we can derive length by counting, which is exactly the principle that was the assumption of bicetal argument, the third assumption. Well, but is it really so that we can say, look, the measure or size of a region is equal to the number of atoms it contains, and from this it follows that the length of a path is equal to the number of atoms contained? Well, Chen says, no, we cannot derive the latter from the former. Why is it so? Well, suppose that you have a three-dimensional space, right? And then the atom has a different shapes, right? That brings it to have a particular unit length along a particular direction, but not along others, right? Then we cannot actually infer the size by counting the length by counting principle from the size by counting principle. Okay? So then there are different proposals in the literature. So one option by McDaniel is to replace assumption 3, the length by counting assumption, with an intrinsic account of distance, okay? And say, well, look, the distance between the two atoms is intrinsic to their fusion, okay? So as long as we have the same atoms and their fusion, then, you know, we can just have, you know, the length. Then another option would be to have an intrinsic notion of a distance between atoms in terms of primitive distances, okay? And so the path-dependent distance between two atoms, okay, is the least sum of primitive distances from one to the other, okay? But then, I mean, all this, it seems rather unsatisfactory, at least to me. I don't want to actually overlook or the salience of these contributions. Of course, they are extremely important. But then the problem to me is, yeah, okay, but then which of these models we have to choose for discrete space, right? So what justifies us in breaking one assumption rather than the others, right? So I think that maybe more work in this direction should be done. And so my proposal is, well, let's turn to physics and let's see if there is some justification for us to break one assumption instead of the others. So then my proposal would be, let's try to look in quantum gravity, which is famous among philosophers of science to be the kind of theory that supports the view that we have some kind of discrete structure, maybe also discrete space at the fundamental level, okay? So then here I will just briefly talk about the canonical quantum gravity, the canonical version of the covariant, even though there will be some pictures inside my talk that are taken from Rovelli's book, which actually, the last one in 2007, where he actually explained the covariant version, but it's because at a certain, I mean, these pictures can be very helpful for us to understand. So, of course, this canonical version of quantum gravity recasts general relativity as a Hamiltonian theory. So, of course, we have a particular foliation, right, of space-time. So, basically, we have a space-time which is our 3 plus 1, so 1 time parameter, okay, and 3 spatial spatial surface. So then basically we have this foliation, right, that is fixed. So we have this 3-dimensional spatial surface parameterized by 1-dimensional time, right? And then we need to do the quantization, okay? So how it works. So first we should find the Hamiltonian of the theory, which is just, we just need to solve the first class constraints, right? And what are these first class constraints? Are the Gaussian constraint, also gauge constraint, and then the formospism constraints or vector constraint, and the scalar constraint Hamiltonian one. So I will not talk about the third one because it's still unclear how to solve the third one. And then for really quantize, right? Well, okay, so we have a general relativity, and in general relativity we have M, which is our manifold, right? And then we have a G, right? Then, which is the metric field, right? So then what we have to do is to quantize G, okay? And then we leave it M as it is. And then here, Smolin and Rovelli really found out the kind of suitable algebra that one has to choose. So unfortunately, I'm not really familiar in the sense I can't really explain the details of this algebra, okay? But basically, we can reformulate general relativity in terms of these so-called Ashtekar variables, okay, which is basically a real SU2 connection, okay, and then we have also a momentum field, a real momentum field, okay, that in some that also Rovelli called the electric field, okay, and then they are both defined on the differential manifold, okay. So, and then they also assume that Wilson loop operators are well defined in the Hilbert space of the theory. And the kind of intuitive picture that is important here is that, okay, so we have to find the Hilbert space of the theory. And so somehow we have to actually get from a kind of space, a Hilbert space of the theory, where we have redundant informations or even like impossible states, to the real physical space where we don't have redundant information, we don't have impossible states, okay? So then we do this by implementing the different constraints, by solving the constraints, okay? And then of course we need to define the operators relevant to the theory, okay? So area, volume, etc. Okay, so what are these constraints? Well, of course, for the Gauss constraints, we require the physical system to be invariant under internal gauge transformation. And what Rovelli and Smolin did was really to do this by identifying a graph of links, which are lines, and nodes, which are the points, right? And at this stage, we are still embedded in our manifold, okay? In our manifold M, which is however stripped by its symmetrical structure. And then we color, okay, we color this graph, right? So we actually put some quantum numbers on the graph, right, in terms of the SU2 irreducible representation and other quantum number, the intertwiners, right? And so basically we have a picture of like the spin networks which are colored, associated with the quantum geometry, right? So of course here we're still in an embedded, okay, spin network, okay, and then to each embedded spin network we can actually associate a unique gauge invariant functional, okay, of the vector, which is the so-called spin network state, okay. And then this is actually serves as our basis of the Hilbert space, okay, which is invariant, gauge invariant, okay. And so then we have other kinds of information here. So we have, for instance, so the quantum numbers which are associated to the links, okay? And then the quantum numbers are associated to the nodes, okay? And then this is the kind of visual picture that we have. Then we have the diffeomorphism constraints, okay, that of course requires our state to be invariant under stretching and manipulation and shifting, okay. And so in order to do this, we actually have to associate to a set of invariant embedded spin network to one unique kind of single state, okay. So we actually construct several equivalent classes of diffeomorphically related states and then associate to each of them a single state, which is the S node. And then we start with the observables. So the observables are built with this intuition by Rovelius-Molin that actually the spin networks are the eigenvectors of the area and volume observables. Okay? So we have the area operator, which is actually defined by the quantum numbers associated to the links, okay? And then we have the volume operator, which is defined by the quantum number associated to the nodes, okay? And the hope or the certainty, I'm not sure, is that the observable area and values produce eigenvalues which approximate the Riemann namespace, okay? I'm not exactly sure, there is a debate if they actually do. Okay, so basically, of course, we can, remove links and nodes, but then what we have here is just a discrete structure, right? Because we associate quantum numbers, right, to nodes and links, so we can remove one node, we can add another node, right? But then we are actually adding and removing units area, okay? So we have this kind of discreteness, okay? And so we can also think of, we can really think in terms of kind of chunks of space, right? So each node defines a kind of chunk of space, and then, we have the links, which defines a kind of area between two regions of space associated to the nodes. And we can keep working with, the dual pictures, which is associated to the graphs, right? And with this dual picture, right, then we can actually understand the length operator. So suppose that here you have really this spin networks with these two nodes, right? And then you have so let's take this node that actually has this link, these two links, right? C2 and C1, right? And then they actually intersect these two surfaces. Then actually the length operator is such that it actually defines and measures this gamma, which is actually this curvature, right? This curve, this curve, okay? So, but the kind of problem with the length operator is that there is still going on lots of discussion about the length operator, and it's still a mess how exactly to understand it. So there are many different proposals about the length operator. Okay, so then what do we get from here? So, of course, why it's a kind of common and traditionally accepted in the literature of quantum gravity to associate volume and area to the elements of the graph, right? Then the kind of ontological picture that we get is quite controversial. So, for instance, Vidotto, in a talk she gave actually at the University of Geneva, she was really stressing the fact that spin networks are just a mathematical auxiliary, okay? So we should not really take them too much seriously when we want to infer our ontology, okay? So the question is how we should then understand the loop quantum gravity space, okay? And then this question is of course important not only if we really believe in loop quantum gravity, but also if we want to have a metaphysics of science that is naturally informed, as informed by physics, right? And so the warning in Rovelli and Vidotto in their book in 2015, even though Rovelli now doesn't really endorse this too much forcefully as he was doing 7 years ago, is that the quantum discreteness here is really due to the discrete spectrum of area and volume, okay? So we have this area and volume that have a discrete spectrum, and this is why we have to think this in terms of a kind of discrete space. But the quanta of space should not be thought as some kind of chunks, okay, that are moving in space, okay? So they say very clearly here, the quanta of space of loop quantum gravity should not be taken too naively as actual entities, okay? So they are saying trying to think too literally in terms of concrete chunks forming the quanta of space can be misleading, as always in quantum mechanics. A pendulum is not made of its quanta. A basis in the Hilbert space should not be mistaken for a list of things. Okay, so they are very clear about this. Okay? However, there is a very opposite interpretation, completely opposite, which is the one developed by Vassallo and Michael Asfeld in the context of Bohmian loop quantum gravity. And they really start from an a priori metaphysical assumption that really the venerable tradition of atomism is the winning one, and the one that we want because of simplicity, okay? And so when we actually try to read the ontology of our physical theory, we should always start with this venerable tradition of atomism in mind, okay? So then what they claim is that no, actually the Bohmian version of loop quantum gravity, which is more or less the same as the one I told you before, it really tells us that there are chunks of space, and that these chunks of space are concrete atoms of space, okay? And they are related by contiguity relations, and that given a set X of n atoms, then we can define an approximation function to a target smooth manifold, okay? Good. So now I would like to present the many substances model, okay? Taking this loop quantum gravity picture, okay? And I don't want to claim that this is the right one, the right interpretation, okay? So I just want to claim that this is a possible reading of loop quantum gravity, and that this possible reading can actually inspire metaphysicians to actually have a metaphysical picture of a discrete space that either has not been put forward before, or that corresponds to one of the violations of the Weissenthal argument. Okay? And so by having this kind of physical informed model of a discrete space, one can actually maybe prefer one violation of the Weissenthal argument assumption instead of the others. Okay? So my starting point is that each so-called atom of space has its own particular decoration, so to say. That is, it has its own geometrical properties that are determined by the quantum numbers associated to links and nodes. Okay? And then I presuppose, okay, I take it as a kind of fundamental fact of the matter that a spin network, okay, has some quantum numbers associated to it, okay, to the nodes, and some to the links, in such a way that a spin network might, for instance, have, I don't know, here I wrote like 8 cubic unit Planck volume, and an area of like 4 square unit Planck area. Okay, so each atom has a different decoration. Okay. So basically, we have a quantum space that is mereological, constituted by many substances, all different from one another concerning their geometrical properties. Okay. And then, of course, this variety of atoms might sound perplexing, right? As metaphysics debate normally assume that atoms are always alike in shapes and in size, right? But is really this something that is forced upon us? I mean, of course, we would expect that our atoms are the smallest possible, right? So such that it's impossible to divide them further, okay? And this would be probably some kind of legitimate expectation. However, I make 2 different notes here. So one is the difference between a theoretical indivisibility and actually what is out there at the fundamental level as our fundamental level of reality in the physical world, in our empirical world. So it's certainly true, right, that once we have a Planck unit, then, we could always say, well, we can have, these chunks of space associated which has this kind of area and volume, right? And then we can always go further and trying to divide it up more and more until we get to the unit, right? But then, this does not imply that at the fundamental physical level, right? We can have different sizes, okay? So we are not forced to say that at the fundamental level we always have atoms with unit Planck unit of volume and Planck unit of area. And this also for this other reason. So actually there are only certain kinds of combination of values for volume and values for area that are possible, not all. Okay, so it can be very well the case that we cannot, of course, combine the unit, the Planck unit for area with the Planck unit for volume, right? So there are different specific ways to combine the values of length and volume and area. So overall, I think it seems completely reasonable to accept that at the fundamental level there are extended atoms with different sizes, different shapes, and that they are mereological atoms, and yet they do not necessarily feature one quantum of area and one quantum of volume. Okay? So the second feature of my model is the notion of adjacency. So the atoms of space are related by adjacency relations, which are symmetric and reflexive, okay? And then they actually play the role of determining locality at the micro scale, okay? So, of course, if two atoms are just at the endpoints of the same length, then they are adjacent, okay? So in this case, of course, contrary to the Weyl argument, then the adjacency relation is not determined by some directions, preferred directions, okay? But it's established by the link, okay? And so they can be, so to say, far away, right? But as long as they are linked by the same link, then they are adjacent, okay? And two atoms, we can say, are adjacent if we have one of their surfaces kind of glued, right? So we have the length that prefers the surface, and this generates the area, right? And then we can say that if at least one of the surface of the two atoms is glued, then these are adjacent, okay? So, of course, the number of adjacent relations for each atom depends on the number of its links, right? So this means that the atoms not only differ for the decoration, as I called it before, but also for the number of adjacent relations. Okay. Then a last thought on individuality. Okay, so we have already said that these atoms might be different one from another, right? But one may even go further and argue that actually these atoms possess adjacency relation essentially. So we have a metrical essentialism, right, in general relativity, right, which is a kind of like substantivalism about space-time, right? And so they say, well, points are individuated by their metrical structure essentially. We could maybe have the same kind of situation here, right, where the low quantum gravity atoms are individuated by adjacency relations essentially. I'm not sure if this works, especially for the dynamics part, okay? So what about the last metaphysical lesson of this model? Well, as we said, one of the big problems within low quantum gravity, the kinematic part, is the definition of the length operator, right? And actually, you know, the notion of length is completely different, right, from the ones that we actually have in our metaphysical models. And it's kind of recognized that it plays just a marginal role, okay, if we compare it to the volume and the area operator. And Rovelli, in his paper in 2008, discusses this at length, saying, well, is it just the technical difficulties, or this is actually telling something about the metaphysics of space? And so one possibility is that actually the notion of length appears as an emergent property, right, in the continuous space, okay, which is not fundamental, but that does not actually appear in any way in the discrete space, okay? So I'm not sure how to look at this. Okay, so some conclusions. So of course I'm not arguing that this is the right way to interpret loop quantum gravity, okay? But I think that this is the kind of a model that is a kind of model that could be carried to the metaphysical domain to give us some kind of novel thoughts about discrete space. And I'm not sure if this model brings more advantages from a metaphysical perspective or not. Of course, it relies on a very different definition of atom, right? So this is the bibliography, and thank you. Thank you all.
All right, Sakshi Dilani with some comments, this time from the University of Geneva.
Thank you, Vera, for providing so much food for thought. And in fact, I think it would be helpful for me to use a reference and some visuals for my comments. So the first thought I had to do with my understanding of the contact between metaphysical characterizations of different spaces and then how we, you know, maybe vet those options from physical theories. So I actually took Weyl's argument to not demonstrate the metaphysical untenability of discrete space, but actually to show that discrete space, and of course we're assuming the atomic part, is empirically inadequate. And that is because our best theory of space is general relativity, and we cannot approximate general relativity using approximate discrete spaces. And that gives us ground potentially to not necessarily force this metaphysical picture. But then we want to see, now that we've identified some assumptions going into his argument, whether we can escape this challenge. And so I see this as being a space of discrete models. So space of models. And you have various options. And if we acknowledge that we can escape Weyl's argument, it's going to pick out a subset of those models. And so with respect to approximating GR, we say that they are empirically adequate. So maybe what, Vera, you wanted to do when you wanted further physical grounding is just empirical adequacy with regards to metrical properties is not enough. There's a lot more about physics that we care about, and therefore we're going to look at some final theory, presumably from quantum gravity, and let's say loop quantum gravity is the best one so far. So then we're going to vet those even further and land on a few discrete models. And now from here, what I take to be the thing going on that we're trying to do is we're interpreting loop quantum gravity, and we have some metaphysical pictures of how that can work, but then to decide between them, there has to be, again, an import of metaphysical virtues to see, you know, what might be the best way to describe our world. So I was hoping you could say something about that, because at least from the paper, I understood your approach to not want to invoke, again, in the process, using metaphysical virtues, and really taking your physical theory as being able to at the final stage, vet which discrete model is the best way to characterize our world. So then the second comment I have is that we have three assumptions in Weyl's argument. So shape and size of atoms. So that's A. B, we have number of adjacency relations. And then C, we have, how do we account for distance? So length by counting. And what I took Bohmian, at least in terms of ontology, the Bohmian interpretation of loop quantum gravity to be doing is to say that these are going to be different. So we've violated the first assumption. These are also going to be different per atom. So let me just specify that. Because the original was that they're the same, so these are going to be different per atom. And then we're going to have some notion of intrinsic distance. And that was a spelling error, but that's okay. So we've essentially violated all three assumptions in this ontological interpretation. And my main question was, in what sense are these independent assumptions? Because from the way we've gone through how the theory is set up, first we determined that the shape and size of atoms are going to be different based on the quantum numbers of the nodes and links. And it seemed to me that it follows from that of course you can't have the same number of adjacency relations per atom, just in terms of how they fit together. It doesn't intuitively seem to work. And then of course, in order to even talk about the fact that they have different shapes and sizes, you need some notion of intrinsic distance. And we're using the length operator as accounting for the intersection of surfaces of atoms that are fused. So it seems to me that it really all seems to fall upon this first assumption as doing most of the work. And I wanted to see what your thoughts are, whether you think these are independent, whether perhaps B and C might be able to be varied independently if you still maintain the same shape and size of atoms, or is A really the main assumption that's going into the argument? And finally, this is a point that you addressed more in your paper, but brought up a little bit in the presentation. So Vidotto and Rovelli's original insistence to not read off the ontology from these abstract spin networks suggests that maybe you can have a model of space that is not atomically discrete. And you say because their interpretation does not conform to the metaphysical definition that we're looking at, you want to focus on an alternative interpretation. And to me, it really wasn't obvious why, even if you want to consider the fundamental things that are going on that's represented by this discrete spectrum of eigenvalues as being modes of interaction or something else, I don't know. It's just not chunks of space-time literally. Why that would still allow you to have an emergent space that's not atomically discrete, because I feel like even if your fundamental ontology is not space, but if whatever it is atomically discrete, then whatever space emerges from that, although it could be a very good approximation to the continuous space-time of GR, should also be atomically discrete. I'm not sure how you could get something otherwise as a derivative entity when the fundamental entity still seems to fit the metaphysical picture that we're discussing. So yeah, if you can please explain why we should take that for granted, that, their insistence that, we can't say as much about whether space is atomically discrete, why we should accept that. So
thank you so much. Thank you very much. So I'll try to address all points. But of course, I'm ready to hear more from you. So yeah, concerning the first question. So my idea of the literature is really that after the Weyl's anti-argument was discussed, right, and it was clear, right, to the community that different models need to be offered, right, for having a compelling model of discrete space. Then, the approach was, okay, these are the assumptions, okay, and then we try to violate one or the other assumptions. And then after that, there is the question of whether these models of space is compatible, okay, with our GR and for me, compatibility, it's not enough to grant a kind of naturalistic metaphysics, right? So even we look in the primitive ontology approach, right? Of course, it's compatible with any sort of physical theories, right? But compatibility, it's not enough. So what I wanted to offer was a thought, well, we should need a guide. We should need some guidance to propose the different models of discrete space, which is not just, okay, we don't want to devise tie argument to make problems, so let's come up with some models of space that is not vulnerable to it. I mean, this really looks an ad hoc, metaphysical kind of approach, right, to the debate. I don't want my model to be vulnerable to Weyl's argument, so now, metaphysically, I come up with some kind of ad hoc models that are not vulnerable. And so my approach is more to say, well, can physics give a new wine, right? For the metaphysics debate with some kind of models of space that might be informed from physics, not necessarily, of course, it might not be the true one, we do not know, but at least has some grounds. So physics can guide us in this process of picking up the assumptions that maybe are violated, right? The assumptions of the Weyl's argument that are violated, right? So that was my kind of approach. So I'm not, of course you will have many things to say. Then concerning the second point, yes. So the Bohmian model, we would say that they have the very same shape and size. So my model will say that they have different shapes and sizes. Okay, yeah. So yes, I definitely think that the three might be well related. I'm not sure if it's actually, like a derivation. In the sense that, you can still have, for instance, same shape and size. So I was getting, so for instance, you can have the same shape and same size, right? And then have an intrinsic notion of length and whatever, okay? And I'm not sure, but maybe you can also have, different shapes and size. And then, probably you will necessarily have a violation of length by counting, but maybe not different adjacency relations. Depends on how you define the adjacency relations and how exactly it's your shape and size, right? I think the kind of relations between the three assumptions is very tricky. You can come up with some models, I don't know, where you have cubes or tethrons, or different, like there is also the Penrose kind of model, and then it's a little bit, and so also the metaphysicians were a little bit, I think, lost in trying to come up with some geometrical shapes that would violate one but not the other, and the third but not the fourth, and the kind of thing. And then concerning the last question, I think
Sorry, 1 minute. Can I have a finger on the second question? So the reason I thought B could not be varied independently of A in your model is because you talked about adjacency relations being essential.
Yeah, in my model, definitely.
To the characterization of each atom. So it seemed like it was actually a part of the shape and size of the atom, how many adjacency relations it had with other atoms. So
exactly, in my definition of adjacency, definitely.
Okay.
Yes.
Okay.
Yeah. Sorry. Definitely. Yes. Yeah. And then I think I didn't get your third question. So here I'm not really. So your question was starting from like Vidotto's kind of clarification that we should not really read off ontology from our spin networks, right? And then at a certain point you asked why then we should, how we can, but in any, so you said something like, well, but in any case you have a discrete structure, right? At a fundamental level, so how we can derive a continuous space as emergent. So this really has to do, I mean, of course, like Vidotto and Rovelli comes from a physics perspective, and then they say, yes, we can recover, GR, and I mean, I'm not exactly sure because I'm not competent in the matter if they actually can do this. I don't know, okay? But they are working out a solution in that regard. Probably what Vidotto was thinking, it was exactly to just put a discreteness in the sense of that we have a discrete spectrum, okay? But then this doesn't tell you that actually we have a space that is really discrete in our metaphysical sense. So in our metaphysical sense, probably we have a discreteness which is really in terms of a granular structure which is really concrete in the sense that we have different atoms. And then she was putting this more in the mathematical kind of side, right? No, it's a discrete because our operators have a discrete spectrum. So I mean, I think that Battista had also like a kind of discussion with Francesca on this point in one of his talks, so maybe he can say something more, but that's what I got. And so then, it's not anymore the question of how exactly metaphysically we can recover continuous space from a discrete space, in the sense we metaphysicians understand discrete space. But it's a more kind of like computational level, physical level of the theory, the physical theory.
Okay, so I agree that unless you take the eigenstate, eigenvalue link very seriously, maybe metaphysically you can't infer too much from a discrete spectrum, but I guess the part that I'm confused about is we still want to characterize loop quantum gravity as being a theory of some fundamentally discrete structure.
Yeah.
No matter how you cash that out.
Yeah.
And you claim that you move on to this second interpretation that's inspired by Bohmian quantum gravity, and then you make it into your own, because you claim that at least the ambivalence that Vidotto and Rovelli express means that they could potentially evade the definition of discreteness assumed in metaphysics, and that's the part that wasn't obvious to me.
Okay, now I understand. Yeah, no, I just meant to say that I don't think that their but their definition of discrete space matches the one that I started with in my talk when I was defining extended regions that are atomic, mereological. So I don't think that we are talking about the same. I mean, that we are not sharing the same definition of discrete space. Yeah.
Thank you so much.
Thank you so much. Thanks.
Okay, let's open it up to questions. So please raise your hands. I'll start with Chris.
Thank you. I have not read your paper. I'm very sorry about that. That's my mistake. But from the talk, it was not entirely clear to me how the interpretation or model, or as you call it, ontological model, differs from a straightforward reading off of the ontology of the spin network, where you have atoms of space or space-time with what you call decorations, the spin representations, basically physically saying this junk has this and this elementary size, it is connected with this other junk, the surface area of the intersection has whatever representation it has, that's sort of the measure of the size. I mean, how is your model different from that kind of reading?
Yeah. So I have a probably different metaphysical import, in the sense that, so the first thing that I want to stress is that it's true that we talk about we talk about Planck units, okay? And so at the fundamental level, we do have a Planck unit, okay? But then, so from what I get in the literature, right? So in the literature of loop quantum gravity, you have different regions, okay, of space that, of course, have different quantum numbers associated, right? But then, when you zoom and then you get at the very first kind of mereological atoms, right? So you get just one node, right? Then that node has associated to it a unit, like Planck unit volume, right? And all have the same unit volume. So basically, it's you don't have at the fundamental level this variety of atoms. So you can have like a region of so you take the spin network, right, and then you focus on a region, right? And then, for instance, this region has like 3 nodes. And then you go even farther, and then 2 nodes, and then you go even farther, and then 1 node, right? So this, I think that for standard, like standard interpretation of loop quantum gravity, these are just mathematical representation, right? That tells you about the volume and the area of a certain kind of region, right? And then within this, right, mathematical representation, you can actually go to a fundamental level where you have just a Planck unit of volume or of area. So that was,
okay. If I can come back, so you said 2 things. The first one puzzled me, and the second one, I mean, so maybe starting with the second point, that, standardly, these are just taken to be mathematical representations. You're not supposed to sort of interpret this directly. That's what Ravelli and Vidotto say at some point. That's true, but I was not referring to that. To sort of, if you just read off the ontology as they suggest you shouldn't, but if you do that, that would then not be a difference to your model. That would be what you would do.
Yeah, sure, yes, yeah.
So there, we're down to the first point where you say, unlike in a standard reading of the ontology of the spin network, you would take these spin representations to be a measure of something physically, namely of physical volume. you just take them to be intrinsically having the same volume and being discernible somehow, yet having some sort of decorations.
No, not me. No,
So-
not me.
Okay.
No, I take them to have different decorations and so different volumes.
Okay.
Yeah.
Okay, so
Yeah.
again, we're coming back. So what is then that different from this straightforward reading?
Yeah,
of
no.
ontology?
So I was just stressing. Okay, so the first point that is different is that I was just stressing that at the fundamental level we have a variety, okay, of atoms, okay, but it's not a difference, okay. It's just a stress, right? It was just stressing that. Then I think that what I was proposing was, for instance, adjacency essentialism, right? As something that I don't think that was said in the literature. So basically that each atom has its adjacency relation essentially, right? And then another thing that I think differs is, so let me go back to, okay, so there is this whole individuality thing, so how we can individuate, and then the adjacency, yeah, and so exactly, so I don't know, but by reading, for instance, the Bohmian loop quantum gravity literature, right? I mean, it seems really to me that they really assume that all atoms are the same. So all atoms are exactly the same with the same size and shapes.
Okay, that's surprising. Do you have a reference for that?
So yeah, it's Vassallo and Mika Asfeld's paper.
Oh, okay.
Yeah. Yeah, so basically I thought, okay, that so I thought that within a very strong interpretation, very literal interpretation of loop quantum gravity, okay, then you still have at the fundamental level, so at the bottom, okay, you still have like these building blocks that are exactly the same, okay, so that you really have the Planck size unit, right, there for, you know, the unit for area and for volume, so that you can really build up the regions from there. And indeed, I thought that I was saying something very controversial. That, so, because of course in the literature of loop quantum gravity, right, you have, you take like your portion, right, of spin networks, and then you say, okay, so, you know, I can mathematically, you know, build the spin networks, and then I can say, okay, this node has this quantum number associated with it, and then this link the same. But then I thought, and then you can just basically carve different regions, right? Out of, once you have the spin networks, you can concentrate on different regions, right? And then you can, I thought you can zoom, right? And then be, you know, more, and until you reach a fundamental level, right? Where there are just Planck units of, you know, for area and volume. Okay, thanks.
I mean, I was just going to just add to this. It strikes me that there's a couple of different ways this disagreement might be going. So it seems like you could think that the volume is Planck size, but the shape of each of the atoms is varying, and shape and adjacency. And I take what you're saying to be that the Planck cutoff is giving you the size of each of the atoms, but not necessarily the shape or the adjacency relations. And then in your view, even the size
exactly.
is varying as well. And you take that to be like going beyond what's happening in loop quantum gravity, and maybe there's a disagreement here about whether that is going beyond what's happening in loop quantum gravity.
I think that's the natural way to reading it. I don't think there's disagreement.
Yeah, okay.
I see.
Yeah.
I see.
Okay.
Yeah. Yeah.
So thanks for this. This was very interesting. I guess from the setup at the beginning, I was kind of hoping you were going to come back at the end and explain how to sort of resolve the volatile sort of problem. But I take it the answer is we don't really know what to do with length, so it's not clear like how to do it. So, but then I was thinking, is there like a version of the volatile argument or some similar, result compared to the Pythagorean theorem for for lines that applies to areas or volumes? That sort of looks like you could set it up in a volatile way, and then so that's a question for you and maybe anybody else in the room that can think of a sort of suitable mathematical theorem that might be kind of turned to a volatile argument, and then you would actually have something that you might be able to kind of try to see what happens, whether the model that you're describing actually solves it.
Yeah, thank you. Yeah, thanks. So actually, my aim is not to show the loop quantum gravity kind of does not violate the Weyl argument, because I don't think that. So Weyl argument was actually developed within a kind of Euclidean space, right? So basically, it would be very unfair here to say, oh look, now we have this loop quantum gravity space, and then this does not is not vulnerable to the Weyl argument. I think it would be a kind of like unfair move. So the Weyl argument was, well, let's take our Euclidean space and let's think that actually it's a discrete, right? Then we don't have any more the Pythagorean theorem, and then it's a problem because we do have the Pythagorean theorem in our Euclidean space. And I thought that the problem of recovering the emergent, like our emergent continuum space, right, from the loop quantum gravity one, it's a different project. So basically what I wanted to show is, okay, we have a model that comes from loop quantum gravity, okay, that can actually give you some tools, some metaphysical tools, right, to actually choose the kinds of models, discrete models that you might want to prefer when we talk about discrete space. So some physically informed new ideas that can actually tell you how we can, go further with, this Weyl argument. And the saying, well, this Weyl argument is not compelling, and look, we have this models of space which are informed. I mean, they, even like loop quantum gravity can help us in supporting this kind of model, right? So that was my aim. It was not really, so the kind of logic of the talk was not to say like, okay, this is Weyl argument, loop quantum gravity solves it, right? It was a little bit more kind of like, thanks.
But it would be nice to solve that, right?
Yeah. Well, I don't know. Rovelli told me that he solved it. So the loop quantum gravity, so that he thought before actually developing loop quantum gravity that was actually a problem. But then he told me, but then it turned out that it was not a problem, that we can recover Euclidean space, and so that's fine.
I know he has a paper where he talks about, these are the two sides of the triangle, so I have sort of, if you imagine, I don't know if this is what he was talking about, you sort of imagine these as commuting length operators, but the idea was this doesn't commute with them, so you just can't add them up kind of in the right way. I don't know if that comes out of the quantum gravity.
As such, she's a
So thank you for clarifying that, because I really thought you were trying to show that by looking at a physical theory first, we can go in the opposite direction and understand which of Weyl's assumptions you don't have to commit to. And so can you explain more why you think it's an unfair move to argue along those lines? Because I took the Pythagorean theorem and Euclidean space to be, okay, we know that even though we don't live in, a strictly speaking Euclidean space, at least locally, it seems like we should be able to approximate it. And that's why we're still concerned about Weyl's tile argument and why this model could potentially show you that actually we don't need any of the assumptions that it starts out with. So can you then maybe explain why you don't think you can go to that extent in the argument you're making here?
I'm not sure if I can't go to that extent, okay? I just thought that it was unfair because Weyl built up his argument really thinking of Euclidean space, how we can think about Euclidean space. And then, as a continuous or, a discrete model. And in loop quantum gravity, we are at a much more fundamental level. And we, of course, we have all the problems of emergence, right? And, of course, you can push the argument and to say, well, no, loop quantum gravity actually shows us, if really Rovelli did actually prove that, we can recover Euclidean space from the loop quantum gravity, then yes, right? But I would feel a little bit uncomfortable because it would be kind of imposing on Weyl's argument some kind of an approach that he didn't mean. Recovering one space to the other, right? While he was just talking and thinking about the metaphysical structure of Euclidean space.
Okay, so maybe I thought that loop quantum gravity was at least a plausible candidate because the diffeomorphism invariance shows that it's, at least in theory we could approximate Euclidean space locally.
It can give you a good case indeed.
Right.
Yes.
Okay. You say emergence complicates the layer
of the argument, and that would be, I think, unfair. It's just that it's not. So I just think that it's not a witty move, right? To claim that loop quantum gravity solves the Weyl argument, because this claim would be vulnerable to the fact that in loop quantum gravity, you're not working with Euclidean space, so it doesn't give you a metaphysical characterization of the Euclidean space. So that's the only reason why I would be very cautious to actually endorse the stronger claim that loop quantum gravity solves the Weyl argument. But thanks for pushing on this point. Thank you.
Yes?
That might be also a bit of a question to Chris, if he's fine with that. So in closed-set theory, right, you have this procedure to discretize space-time in such a way that this is d'accord with local lower invariance in some sense, right? I'm just wondering whether I could use this to argue with such a kind of springing, but also get for some limit local Euclidean behavior for the discrete scheme. We normally would think so that for small velocities, so to speak, whatever this discrete really means, you have the kind of Euclidean transformation after all, rather than a strictly Lorentzian anymore. So I don't know whether you have pretty on the spotlight here, but Chris, maybe you have something in this direction. I
I'm not exactly sure what the question is.
The question is basically whether basically the discretization scheme of space-time in the way how you do it in concept theory could be a way to kind of square the issue with Weyl's style argument, that you have a discretization which is fine with this local Euclidean structure actually.
Sorry, can I just make a suggestion that we keep
Oh,
focus on
okay.
the speaker and maybe
Okay,
you guys can
yeah.
follow
Yeah,
that.
okay, sorry, okay.
Malcolm.
Yeah, I have a clarificatory question on
Yeah.
something that you said at the beginning of the
Yeah.
presentation, kind of. And then maybe you mentioned also when explaining the Sarles
Yeah.
idea. So you said that you have like this conscious of space that should be understood as concrete
Mhm.
and I mean, this kind of puzzles me because like when you talk about discrete space, you don't need to specify that the atoms of space are concrete entities. And, like on the contrary, this could be kind of misleading also. In a
Yeah.
sense.
But you
So,
mean
yeah,
about sorry.
So yeah, basically my question is
Yeah.
if like with concrete you mean just something that it's useful to distinguish it from the idea that they are just mathematical artifacts,
Mhm.
or it's something more like a more developed notion of that.
Yeah, thank you. So here, as I said in the beginning, I'm really taking the atomistic discrete view of space, right? Where they really talk about kind of like extended regions of space, okay? And then, so they really mean something spatially extended, okay? And yes, I just wanted to make the contrast, right, between, just a kind of mathematical object that is there, and what I meant by concrete is really something empirically accessible, at least in principle, right? So with concreteness, I meant that. Yeah. Thank you.
So, Enrico?
So, thanks, so Vera. Just as a thought that I have here. So, in this kind of primitive ontology interpretation of spinnet, right? I suppose that Bohmian primitive ontology inspired thing. Ultimately, you don't expect a like superposition of these spinetics, right? You always expect to be some eigenvector of the eigenoperator, ideally. If this is correct, how do you actually, this actually was asking something on these lines before, how do you actually get areas out of that? Because if I understand correctly how they do this in loop quantum gravity, like generalistic areas.
Yeah.
If I understand correctly how they do this, they basically take these massive superpositions of spinetta states, and they're like, okay, when we take this massive superposition, we get back general relativity. And you don't get back general relativity in this approach?
Yeah, indeed. I mean, this is why I think that the atomist, like the model that the Bohmians and that I presented, has all these sort of problems, right? That if you have to eliminate all, to a great extent, all the mathematical structures about superposition, right? And fuzzy geometry and so on and so forth, right? That actually you need, right, to then work out the physics of your theory, right? So this is why I don't want to endorse this particular model as the right model for loop quantum gravity, right? So I'm not, as I made it clear, I do not want to claim that this is the right model for loop quantum gravity. I think Rovelli has the very same criticism against like the idea of Vassallo and as well to take all the superposition to be just in the mathematics and that do not correspond to any physically like superposition state, like physically real superposition state and so on and so forth. Of course, you have this big gap, right, between your mathematics and the physics. And this is something that, for instance, the primitive ontology approach would just be happy with. and they would say, yes, okay, we have, this area, it's just, how can I say, like read off, right, at a certain point, but then we take all these superposition states to mean nothing. Yeah, I mean, of course, this is not the kind of move that we would think of a reasonable, natural, informed metaphysics of science, right? I mean,
We're running short of time, so I just want to get to Lucy.
sorry.
Maybe my question's a bit vague, but I'm just wondering if you have kind of hopes that this overall picture can be extended to include dynamics once we have a good
Yeah.
solution to the Hamiltonian constraint.
Yeah, actually, I didn't work into the dynamics, and I'm really afraid that, for instance, the kind of adjacency essentialism will not work because you have spin networks. You have movement of spin foams, and this kind of thing that I didn't work out. But yeah, I suspect that it might not work.
So this is just kinematic?
Yeah, this was just the kinematic, and even not, yeah. So it's just the kinematic for the canonical one, yeah.
Thank you.
Yeah, thanks.
I wanted to ask a quick question. So, in a few places with respect to kinematical stuff, Ravelli talks about how the sort of approximation of GR is similar to what you do with the Reggie calculus, which is like sewing together simplexes. And so when you talk about the shape and size of the atoms, this is a genuine question, I don't know. Is it the case, do you think, that the shape, although you might have different simplexes, it's still a kind of symplectic, like the atoms are still symplectic in the way that they are in the Reggie calculus, or is it just a kind of it just numerically agrees with Reggie calculus insofar as you get to a similar point, like with the values for the output of what you end up doing?
Yeah, I genuinely do not know. I suspect that it's kind of like it might approximate, or but yeah, I genuinely do not know.
Yeah, I don't think it matters that much, but like the sort of different shape and size, it might be. It's still different because like triangles are different to pyramids, right?
Yeah.
So it's sort of different shapes.
Exactly.
But like there's still a type of shape that might be important, and I've never quite understood with Luke quantum gravity whether that matters.
Yeah.
I think it's not related in the sense that the Reggie calculus is just an intermediate step. And they explicitly say that the discreteness at least doesn't come from the Reggie calculus. So I don't know.
Yeah, no, I get that, but he says it sort of gets you to like there's sort of analogies between what the way that you get to the sort of approximation of GR and the way that you get to the approximation of Reggie case. And I wondered if the analogy was like purely mathematical, but if there was something in the actual like shape stuff, like the sort of symplectic, whether there was something symplectic about Luke quantum gravity, basically.
Yeah, thank you. Yeah, I don't know.
Yeah, I don't know.
Yeah, so thanks. Yeah, thank you.
Okay, please join me in thanking Vera.